Thank you for the opportunity to speak here today. I will speak today about stationary random entire functions and related questions. And in fact, I'm going to present 3 projects. So the first one is called stationary random entire functions. And this project is based on a joint work with Lev Buchovsky, Alexander Loganov, and Misha Sodin. It's basically the main part of my PhD. And then 2 projects that are related, but independent completely, that I finished in the past 2 years. So one is recurrently bounded function, and the other one is frequently oscillating functions. And you will see that they are very strongly motivated by the first project. All right, let me start with the first project. And I'd like to start with the motivation. So if you taught lately complex analysis, this question should be quite trivial for you. Does there exist an entire function with 2 independent periods? It's very likely that people don't remember if they haven't taught the course lately. But the answer is no. And the reason is, well, let's assume that we did have two independent periods. Then together they form a non-trivial fundamental parallelogram. And this parallelogram tiles C. So that means that every point in C, you can take, say, n translations of Z1 and m translations of Z2, where m and n are integers, and bring this point inside this parallelogram. And if the function is invariant under Z1 and Z2, this means that for every point in the plane, there's another point in this parallelogram with the same value. So the absolute value of f, its maximum is bounded by the maximum of the absolute value of f inside the parallelogram, and this is finite. So by Liouville, this is going to be a constant function. Well, what about a translation invariant metric? So apparently there can't be a translation invariant metric. And the reason is, well, first of all, what I mean by a metric, I mean a metric that generates the same topology as the local uniform topology. So the topology that you get from convergence of sequences uniformly on compact sets. And the reason is, well, we know that the series e to the z minus n converges locally uniformly to 0. So on one hand, as you see here, the limit of the distance between the two has to tend to 0 if this metric forms the same topology. But on the other hand, if this metric was translation invariant, then the distance between 0 and e to the z is the same as the distance between 0 and e to the z minus 1. And by induction, it's the same as the distance between 0 and e to the z minus n. So we get that the distance between 0 and e to the z is 0, but this means that e to the z has to be equal to the function 0, which is something that we know it can't be. It's not true. So we can't even have a translation invariant metric. Well, maybe we can do something in probability. Can we create maybe an entire function which is random and it is translation invariant by law? Now, this is a kind of hand-wavy way of presenting things. So let me first present a few definitions, and then we can actually formulate this question more accurately. So what are the objects at play here? Well, the group C is acting on the space of entire functions, which I will denote by curly E, by translation. What is a translation? Well, for every point in C and for every entire function f, the translation of f by w is going to be the same function f, but instead of evaluating it at z, I'm going to evaluate it at z plus w. It's like instead of looking at our plane from the point of view of the origin, you're going to look at the plane from the point of view of w. And a probability measure on the space of entire function will be called non-trivial translation invariant probability measure. If it's not supported on the constant functions, this is why we call it non-trivial. But also, for every measurable set, the measure of the set is the same as the measure of the pullback of the set by a translation. So the pullback of a set by a translation is just this set. So you take every function in A and you apply t minus w to it. So notice that every such measure actually gives rise to a stationary random entire function. And in fact, every stationary random entire function creates such a measure. So you have 2 descriptions of the same thing. Okay, so now let me get back to the question I asked. Is it possible to create a random entire function, which is periodic by law? But formally what it means is just there exists a non-trivial translation invariant probability on the space of the entire function. And for sometimes it wasn't clear what the answer should be because we don't have a translation invariant metric even. There's, in a sense, there's no place to start. But then in 1997, Weiss showed that there are many different measures or processes with many different dynamical properties. And he asked about the minimal possible growth of functions in the support. And the growth of an entire function is measured by the asymptotic behavior of this function, this m sub f of r, which is just taking the maximum of the absolute value of f over the boundary of a disk of radius r. And basically every one of these projects that I'm presenting today will be about bounding this quantity. In the first project, it will be for entire functions, but later on we'll use the same notation for subharmonic functions. Okay, so
Adi?
Yes.
Could you please explain why Benji asked this question? I mean, why would he suspect that it's not a continuous? Why would there be a gap, say? Or
you mean why did he ask about the
minimal growth? I mean, why wouldn't it be just the constant as functions of the minimal growth?
So he was asking about non-trivial measure. He was asked about non-trivial measure.
Yeah, but if you have such a continuum of such measures, then it still could be that the minimum is just a constant function. So,
well, okay. So let me continue a little bit more, one more slide, and then I think this question will be answered. And by the way, it's hard for me to track also the chat. So Boris, if someone has something on the chat, if you could please tell me. Thank you. All right, so I'm sorry, we'll take 2 slides. So first I'll state the result, and once I'll start explaining what we did, I think it will be more and more clear why there's a problem with the growth, in a sense. So in a joint work, as I said, with Lev Buchovsky, myself, Alexander Loganov, and Misha Sodin, we gave a nearly optimal answer. On one hand, if you are given a non-trivial translation invariant probability measure and you sample an entire function from its support, then almost surely this function has to grow like, at least like an exponent of logarithm to the power 2 minus epsilon. So this already tells you a few things. So first of all, this is very interesting from a few different aspects. Usually when people are dealing with entire functions, the most common object to deal with are what's called functions of exponential type. So functions that their growth function is bounded by an exponent, some exponent. And here we have an exponent of an exponent. So it has to grow really, really fast. And also you can see that there is some abstraction that actually imposes restrictions on the growth. And on the other hand, we also constructed a measure where almost every function in the support has to grow like an exponent of the power 2 plus epsilon. Of course, there are constants involved. And also these epsilons here, you see, I show that for every translation invariant, this limit holds for every epsilon, and for our construction, this thing holds for every epsilon. The correct term is, well, this should be log squared and then powers of lower logarithmic terms. So log squared or things like that. It was just simpler to state it like this. And I'm saying that it's nearly optimal because we have minus epsilon for A and plus epsilon for B. It's not clear where to classify 2. Okay, so let me say a few words about the construction. From here, it will be clearer why there should be some abstraction on the growth. So we use the classical Krylov-Bogolubov construction. What does it mean? You take a sequence of sets that saturate the space, and one element of your space. In our case, it will be a function f, and you define a sequence of probability measures. So to measure the set A, UN, what it will do, it will take the average of the points W in Sn, such that TW of F falls inside of A. So in a sense, you take the restricted orbit of F, you see how much of it lies inside A, and you normalize. And if this sequence were to converge, and if the limiting measure would be not supported on infinity and not supported on constant functions, then great, we've made it. But the problem is the space of entire functions is not even locally compact. It's not clear that we have a converging sequence or a subsequence. And if you think about it for a little bit, you see that if you take, for example, f to be any polynomial, the limiting measure that you get is going to be supported on infinity. So we need a special function for this, which I'm going to call self-similar. Now what I'll do now is I'll give like a vague explanation of what is self-similar, and then I'll bring a construction, but I will not give a precise definition. Basically what a self-similar function means is you have a sequence of nested cubes where for every cube, you can take 9 copies of the previous cube and place them quite tightly packed so they don't touch each other, but the spaces are very, very small. And f will look almost the same on every cube. So we know it can't look exactly the same because of uniqueness theorem, but it's going to be like a perturbation of itself. So to construct this, we started with constructing a counter set, what we called an inside-out counter set. What does it mean? Well, I start with this cube here, this small cube, say it's -1, 1 squared. And I take 9 copies of it, and I place them evenly spaced according to some law inside this cube. So this will be my second cube in the sequence. And then I take 9 copies of this structure, and I'm placing them evenly spaced according to some law. And you see I have very, very narrow corridors, and I have these cubes. And formally, after k steps, if I want to create ck plus 1, I take 9 copies of ck. I place them evenly spaced according to some law, and the union will be ck plus 1. So then how are we going to construct our function? I'm going to start by defining the function on this tiny cube here, and then I'll copy the definition here, and I'll paste it. So for people who taught complex analysis lately, we can use, for example, Runge's theorem to paste it. We're going to use something stronger because Runge doesn't give you bounds on the growth, but there are all kinds of techniques. And when you paste, what you get is that in every cube here, you get a perturbation of what you placed there to begin with. And in the corridors, you don't know what's going to happen. So then in the next step, I'll take the definition of f here, I'll copy it to the other cubes, and I'll paste again. The further away I am, so on ck, for example, I'm going to allow less perturbation. So I'm going to ask that this pasting distorts my function less. But this costs in growth, so I pay in growth. The second thing that contributes to the payment of growth is how wide these corridors are. So the relative measure of these corridors inside the bigger cube. But if you choose your parameters correctly and you do everything gently, then you can get the optimal growth that I presented earlier. So it's this self-similarity and the pasting that tells you that you can't really have a smaller growth in these functions, right? That's the answer to your question, because it has to be self-similar. Okay, great. So I'd like to put a pin on this construction because I'm going to get back to it. And we're now going to the second project, which means that if somebody lost me during the explanation, this would be a good place for a recap. So the self-similarity property inspired a few questions. And the first one is about recurrent sets. So what's the deal with recurrent sets? Why are they related? Well, there's a theorem by Hermander that basically allows you this gluing thing I was talking about with controlled growth. And it relates the zeros of entire functions, the zeros of subharmonic functions with pre-assigned values of an entire function. So you have an entire function, and it's You predefine it in some subspace like we did. And then when you want to paste it, you're going to use some kind of subharmonic function, and you're going to use the zeros of these subharmonic functions. They should be in the same place where the pre-assigned entire function is. In any case, this self-similarity property that I discussed earlier, it got people interested in self-similar zero sets of subharmonic functions, or subharmonic functions such that their zero set is self-similar. And this inspired the following definition. So a set E will be called epsilon r recurrent if for every x, you look at the measure of E inside a ball of radius r of x. And the relative measure is going to be bounded from below by a function of epsilon. So the picture you should have in your mind is this. So while before the cubes were kind of tightly packed or neatly packed, you see that here we allow some freedom about the distribution. So the function r is going to be responsible for the distribution of the set, how wide these annuli are, and the function epsilon is going to be responsible for how big these blobs are. I find this picture perhaps mildly misleading because even if epsilon is monotone decreasing, it's not necessarily that these blobs shrink, because r is increasing, so you have this balance. One remark for the experts: the real definition is not with Lebesgue's measure, it's with capacities. So I'm using logarithmic capacities for dimension 2 and Newtonian capacities for higher dimensions, where the normalization I'm using is the one that gives the capacity of a ball is going to be its radius. So the theorems I'm stating here, they're somewhat weaker than what I actually have. And again, we are interested in the minimal possible growth. So the fact that you always have these zeros pulling you down and kind of nightly distributed, it's gonna cost you in growth. And the question is how much? Okay, well, first, for people who are not experts in the field, why are we suddenly interested in subharmonic functions? So we all know that entire functions are great, right? They have a lot of really nice properties. They have smoothness, they have representation as Taylor series, uniqueness, maximum principle, Liouville theorem, Cauchy integral formula, a lot of really nice things. And there's a very strong connection between entire functions and subharmonic functions. It's not precisely one-to-one, but if f is entire, then log of absolute value of f is subharmonic. And sometimes for subharmonic function with nice properties, you can use this Hermander theorem I mentioned earlier to get an entire function with similar nice properties. Well, the fact is that this relationship in particular tells you that, well, a lot of the nice properties that entire functions have, maybe they also pass to subharmonic. So some of them do, for example, the maximum principle. On the other hand, subharmonic functions are a lot more flexible. So when one tries to bound, for example, the minimal possible growth of entire functions with some recurrence property, a good place to start is to investigate the minimal possible growth of subharmonic functions with a recurrent zero set, which is precisely what we're trying to do. So what were we trying to do? We were trying to, find the minimal possible growth of subharmonic function such that their zero set satisfies this. So they have a lot of zeros and they're distributed according to R, and how big these blobs are, it's controlled by epsilon. Now, this nice kernel here allows me to formulate one theorem for all the dimensions altogether. So kd minus 2 will be log t if d is 2, and minus 1 over t to the d minus 2 for bigger d's. For those of you who try to understand why why did I use the notation d minus 2 here? This is just, this is what is the notation is used in the field. And using this kind of phi, we see that on one hand, if the lim sup of 1 over t phi of t is bounded by 1, and u is subharmonic, has an epsilon r recurrent 0 set, and is bigger than 1 somewhere, then it has to grow like an exponent of the integral of phi. And on the other hand, we have the other side. If the derivative of 1 over phi is bounded, then we can construct a subharmonic function in RD whose 0 set is recurrent. At 0, it's bigger than 1, and its growth is bounded from above by an exponent of this integral. So we get an upper bound and a lower bound. And I'd like to say a few words about these conditions. So I have a condition for the upper bound and a condition for the lower bound. For the lower bound, we require basically that phi of t will be bigger than 1 over t for large enough t's. Well, this is for the experts in the audience. This does not yet coincide with Wiener's criteria that will say that, you know, I can get a minimal possible growth, which is logarithmic in dimension 2. But it's a very weak condition. So for example, if r of t is proportional to t, then you can take a rescaling of this kernel here and you get the aspired function. So it's not going to be interesting. So we're only interested when r is strictly less than t, so little o of t. And then, for example, for dimension 2, basically, if you take epsilon to be 1 over any polynomial, this would work, even exponential. If the power of the exponential is small enough, that would even work. And the same for this case. So even though our assumptions don't coincide with Wiener's criteria, they're not that far away, they're not that restricting, and the bigger the dimension is, the bigger the gap becomes between the condition that I impose and the condition that Wiener's criteria imposes. Well, we have a similar result in the setup of Brownian motion. So let me say a few words about what is a Brownian motion, even though I'm sure most people know, but let me just give you a reminder. So we look at a set, for example, this set in the picture. I drew the inner boundaries in red, the outer boundary is black. And Brownian motion basically describes the movement of the particle starting from this dot inside omega. And once it hits the boundary, it's going to die. So it can only move around until it dies. And in particular, we're interested in the probability that this particle dies at some specific part of the boundary, not somewhere. And for experts, this is precisely the harmonic measure of this domain. And this is the relation with subharmonic functions. This is why these are two companion results in a sense. Okay, so in the setup of Brownian motion, we're trying to ask the same question. So now the question becomes, well, let's assume I have an epsilon r recurrent set spread around space, and I take some large ball. What is the probability that a particle starting, say, from 0 will die hitting the outer boundary and not parts of E, not the things inside? So let phi be as before, and B rho is just a ball radius rho, which is open. Then under the same condition I had earlier, we can find constants such that for every epsilon r recurrent set, if you look at the probability of a Brownian motion starting from 0 in the ball, once you removed E, to hit the boundary of the ball and not E, it's bounded from above by this expression. And on the other hand, if the derivative is bounded, then I can find constants and a recurrent function such that every Brownian motion will also have a probability which is bounded from below by the same amount. So the constants are different, but the asymptotic behavior is the same. And the reason I'm stating this here, well, these are actually, in a sense, two companion results. So I prove, I prove A here and B in the other theorem, and then I show that these theorems are related. But I want to present a few arguments, or like intuitive argument, why A holds, and And the intuition comes from Brownian motion, from probability. So usually what happens in this case, when you're trying to estimate Brownian motion starting from some point, you try to avoid a bunch of obstacles. These obstacles are the set E. What you would do is you would group together parts of E, and then you'd say, okay, to pass this group, the probability is this. To pass that group, the probability is this. And then you're going to hope that these parts are not going to interact too much. They will not be independent, but the dependence will be weak. So the probability to pass the whole thing will be roughly like the product of probabilities. So think of it this way: you're in a concert of Shakira, and the stage is in the middle, and you're way, way back at the rim, and you're trying to devise a scheme to cross all this very, very dense population of people. So in your brain, what this would look like is this. Oh, sorry. Right? You take the entire whole, you split it into layers, and you say, okay, to cross the yellow layer, the probability is this. And then to cross the orange-yellow, it's easier to estimate these probabilities just because they have less obstacles. They're local, they're more local. And then if the, for example, orange and red layers have dependence, which is very weak, say it only decreases the probability by some very small amount, then you can bound the probability to cross both of them by the product of probabilities times perhaps a small constant. In fact, what you should be looking at is this, because the origin is where you are, and the destination is where Shakira is. And what's interesting about this result, so there are two very interesting things. The first one is, like the average person who goes to a show, the experts predicted that it will be enough to bundle together, say, finite number of annuli. So if you bundle together, for example, 10 layers, and then you say they will weakly interact with the next 10 layers. So maybe it won't be 10, maybe it will be 100 or 1,000 or some big constant M. But the fact was that the number of layers to bundle together in order to get this independence, this weak dependence, is actually a function of epsilon. So it's this thing. Minus the kernel composed with epsilon, where the kernel, I'll remind you, in dimension 2, it was just log, and in higher dimension, it was -1 over t to the power d minus 2. That was surprise number one. So I do use the same technique of splitting it into layers and bounding the probability on each layer, but the interesting thing is the number of layers you need to bundle together. The second interesting thing about this result is that in this field, usually you have one kind of proof for dimension 2, and then a different kind of proof for higher dimensions. And there are two reasons for it. The first reason is this kernel that I just told you. I just reminded you that in dimension 2, you have log t, and in higher dimensions, you have -1 over t to the d minus 2. So these are different kernels with different properties, but more than that, the biggest reason is in dimension 2, we have complex analysis on our side. So you have a lot of tools that you can use from complex analysis, Riemann mapping theorem, all that kind of stuff. In higher dimensions, we don't have these tools. So you have to find, in a sense, a workaround. Now, with the notable distinction of Peter Jones and Nikolai Makarov's work, their paper is called Density Properties of Harmonic Measures, and also a recent work by Chris Bishop about Weil-Peterson curves. I did not encounter any unified proofs. And here we present a proof, which is just one proof for all the dimensions. We didn't distinguish between them or anything. So that's also nice. Okay, so this brings me to the last project. And I told you that both projects are going to be inspired by the first work. So let me remind you, what was the theorem? So I was visiting Stony Brook on my postdoc tour, and I was talking to Chris Bishop, and I presented my work. And what bothered him was this. Now I'm half making a joke out of it, but it was very, very likely that this epsilon is redundant. I will mention later that the other epsilon is not really redundant, but this one, it felt like it was really just an obstruction of the methods we were using. And after I left, we had numerous emails whether or not this paper that I mentioned earlier of Jones and Makarov could maybe assist resolve this issue. And this inspired a very big project that I will describe now. And in the end, this will be a corollary of the more general thing. So as always, we should start with a few definitions. A cube I will be called a basic cube if it's half open, half closed, and the vertices lie on the ZD lattice. And given a subharmonic function and a basic cube, I'm going to be interested in two properties. So property P1, whether or not the supremum of U is bounded from below by 1. And property P2 is if I look at the zero set of U, and I look at the d-1 Hausdorff content of the set inside this basic cube I want it to be bounded from below uniformly. So uniformly because this delta D here does not depend on I. And every cube that doesn't satisfy either one of these properties, I'm going to call it a rogue basic cube. So after listening to everything that's happened so far, the natural question should be, well, obviously, this lady here is interested in growth. And then we have these rogue basic cubes. What is the relation between good basic cubes and growth? So we have the following observation stating that there is a constant which only depends on the dimension, so that for every subharmonic function defined in a neighborhood of the unit ball, if the Hausdorff content of the zero set of U inside half the ball is bounded from below, then the function has to jump. What do I mean when I say jump? The maximum of the function is bigger than the value at the center of the ball times some constant which is bigger than 1. So it's e to some power which is greater than 0. And this power is this constant CD times epsilon. So there's a very natural correspondence between the epsilon and how much we jump. And I'm going to call these jumps.
Adi?
The jump in growth. Yes.
I have a question about property 2. It's not clear to me the definition because you take also the open set U smaller than 0, then this will always give you, unless U is positive in some cube, then this will always give you, I mean, d-1. It will give you an infinite d-1 measure, right? Or I didn't understand. Can you go back one slide, please? Yeah, in property 2, so if you consider the set U where U is negative, then this is an open set, so it has a d-dimensional measure volume. So what do you mean?
First of all, I think it's a closed set because it's an intersection of two closed sets. If U is continuous.
Yeah, but it contains the open set where U is negative.
Yes, but
so if you change its sign in one cube, then this is automatic, no? Or something I don't get in this definition. No?
Okay, so this relates to stating things in a stronger version that then, like, maybe it would have been clearer if I would put here Lebesgue's measure, and it would also be true, but it would be a weaker statement. Because if you also consider sets where U is 0, not negative, then these could be just lines, for example.
Yes.
Right? And then these lines would have a d-1 content, which is finite.
Yeah, that's fine.
Right? So when you think of this property, you should not think about the easy case where you have a lot of zeros and a lot of negative things, but about the more gentle places where you just have a tiny, tiny string of 0. Right?
Yeah, okay. So you're basically you are saying that the interesting cubes are where U doesn't change sign, but it can get to 0 or something. Yes, and you have.
First of all, for subharmonic functions, sometimes it's easier to just because the maximum of two subharmonic functions is also subharmonic, it's very common to just take the maximum between your function and zero. And then your zero set is actually, this is why I call this set u less or equal to zero set. Because as you said, it's not only zeros, it's also the negative values. But yes, in a sense, what I say here is you don't even need to have an open set where it's negative. It's enough that you have like these very fine kind of sets.
Yeah, okay.
So is it okay just to say zero? You were saying zero set, but writing less than or equal. One can just think about zero sets?
Yes.
Mm-hmm.
Yes, one can just think about zero sets.
Mm-hmm.
Okay, so we had this observation about jumps, and I will describe a little bit of history. Basically, everything that was done uses this observation and just counts how many times I can use this observation to get the lower bound that we want. So now that we've established that good basic cubes are going to make the growth worse or bigger, depending on your point of view, I guess, we are ready for this definition. So if I have a monotone non-decreasing function f, which is bounded by the area, and a subharmonic function u, I will call it f oscillating if the number of rogue basic cubes can be bounded by f for large enough cubes. Right? So for every large enough f, the number of basic cubes which are rogue in minus n to the d is going to be bounded by f of 2n. And as before, I'm interested in the minimal possible growth of these things. So what was already known when I started working on this? Well, in dimension 2, if f is equal to 1, so f is equal to 1 means that the number of rogue basic cubes in every cube is strictly bounded by 1. I have no rogue basic cubes. All the basic cubes are a grid. So I can apply this argument, this observation that I mentioned, for every cube. And so you get an exponential, which is growth. The growth, is exponential. And this is something that already appeared in that joint work that I mentioned at the beginning of my lecture with Bochovsky, Loganov, and Saldian. Well, another case that we considered was actually on the other side of the spectrum. So again, in dimension 2, but now f is, in a sense, the area function. So f of t is t squared. And there we showed in the same joint work that the optimal growth is going to be, so it's going to be bounded from below by an exponent of a constant of log to the 2 minus epsilon. And we also gave a construction with c log to the 2 plus epsilon. But now the question is, well, what about other functions? So these are two extremes, right? No rogue basic cubes or so many rogue basic cubes that they're proportional to the area. What about anything in between? And more importantly, is this epsilon necessary? Because it's a bit annoying. So we have optimal bounds now. Let me start with a simpler case. Let's assume that f is just a power of t. So alpha could be any number between 0 and d, the dimension. And I define phi f of r to be r if alpha is less or equal than 1. And if alpha is bigger than 1, it's going to be this little monster. So r to the power d minus alpha over d minus 1 times log of r to the power d over d minus 1. And the first part of the theorem states that there exists a constant. This constant depends on the dimension, but only on the dimension. So that if f of t is less than this constant times t to the d for t large enough, then every f oscillating subharmonic function u has this to grow at least like an exponent of this phi. So if alpha is less or equal to 1, it's going to be just exponent of r. And if alpha is bigger than 1, it's going to be exponent of this guy. And on the other hand, for every function f, we can construct an f oscillating subharmonic function u so that it grows at most like an exponent times a constant times phi. But truth be told, I can actually show something a bit stronger. So I can show the same thing for almost every what's called regularly varying function. So a regularly varying function is a function that is a product of t to some alpha times G, and G is slowly varying. So slowly varying is, think about things like powers of log, or things that are just, they may tend to infinity, but they don't change that much. But then the function phi f is this thing. So this looks a lot more intimidating than what I presented earlier. This is why I prefer to present it like this. For the construction to hold, we do need a small additional condition that if alpha is less than D, there's no problem. But if alpha is equal to D, then G has to be monotone, non-increasing. So you can't have too many oscillations. Or if you do, you'll just have to figure out some kind of a function to somehow be an upper envelope for G and will be monotone decreasing. Okay, and in fact, as a corollary, we get that if I take you back to the optimal bounds, excuse me. If we look at this function now, and we take D equals to alpha equals to 2, then this component vanishes, and this component is just log squared. Sorry. And so this epsilon here was indeed redundant, and I promised I'll say a few words about this epsilon that is here to stay. Well, most likely. This epsilon comes from something like the convergence of harmonic sums. So we know that harmonic sums are divergent, 1 over n. But once you add something small, log squared, it will already converge. So this is where this additional epsilon comes in, and it's probably there to stay. Okay, so let me say a few words about the lower bound. Let me bring back this observation that I told you that all the proofs basically count how many times I can use this. And we assume that U is subharmonic in a neighborhood of the ball, and that the D-1 Hausdorff content of the zero set inside half the ball is bounded from below, and then we get the jump. But in fact, what we're going to use here, we're not going to see how many times I can use this observation for one particular point. I'm going to try and figure out how many times I can use this observation simultaneously for a collection of points sitting in a collection of basic cubes. So for every basic cube I'm going to look at a sequence of cubes concentric with I, so they surround I. And I'm going to choose a subsequence of these cubes, Cj, such that every point on the boundary, I can find a radius, RxI, satisfying 2 conditions. The first condition is if you rescale U by RxI and move it to the origin, then this holds, so which is exactly this. So the condition of the observation is it holds and I may use it. And on the other hand, I want that this ball surrounding psi of radius psi is contained in the next cube. This means that if I have a lower bound on the maximum of this ball, it's going to bound the maximum of the cube from below. And because if I have these 2 properties for every point on the boundary, and we know that the maximum of U is achieved on the boundary because of the maximum principle, then in particular, I can use this observation to conclude that the maximum over Cj times this extra jump, this exponent to the power Cd times epsilon, bounds from below the maximum on Cj plus 1. And when you apply induction, you get that the maximum over the entire cube is bounded from below by the maximum over the basic cube times an exponent of some power, which depends on the dimension, times the number of times I was able to apply this observation. So now all that is left is to see if there are enough basic cubes which are good. So this maximum here is 1. And also this component is big. And here we use various combinatorial methods that are inspired by that paper that I mentioned by Jones and McCarve. All right, let me talk about the example, because the example is I find it very exciting. So I was very happy to use this. Remember, I told you to put a pin on this example. We had this self-similarity thing, and I really wanted to use it again, but I can't. And there are 2 reasons for that. Well, the first one is precisely this expression, self-similar. So we have a version of this for subharmonic functions, and in the subharmonic version, the function actually looks exactly the same on every cube. Not a perturbation, but let's assume I have 1 rogue basic cube, say in C2, in this. Well, if I use this self-similarity, it means in the next step, at least in dimension 2, I'm going to have 9 of those. And in the next step, I'm going to have 81 and so on. In dimension D, you get 3 to the D, 3 to the 2D, and so on. So it's proportional to the volume. So every function which is strictly less than T to the D, this would not work. And even for T to the D, you don't get the optimal bound. That was one problem. Well, they say, well, you can still use the same techniques, right? Just don't pre-assign something else. Well, we still have a problem, because in dimension 2, we can't really see it, because in dimension 2, these corridors where the rogue basic cubes are going to live, their measure is proportional to the length times some small interval, right? So it's order of T. And it's okay, because if alpha is less or equal than 1, that is, my function f is like T or less, anyways, the growth is exponential and we're doing something else, so it's not interesting. But if you go to higher dimensions, think, for example, about a Rubik's Cube. You have a Rubik's Cube, and you think about the spaces between layers there. They're going to be like very, very thin sheets, 2-dimensional, times some small interval. So they're going to have at least T squared rogue basic cubes. And if you go to higher dimensions, these walls that split between different cubes are D-dimensional, D-1 dimensional hyperplanes. So they have measure which is proportional to T to the D-1. So this could not work if f of T is little o of T to the D-1. So what can we do? So what I'm going to do now, I'm going to present the support of the function that I create. So it's where the function is not 0. And I'll start with dimension 2 because it's easier to draw, but then I will have a 3D demonstration as well, because the difference between tubes and hyperplane times an interval in dimension 2, it doesn't exist, right? It only exists in higher dimensions. So we start with dyadic cubes of rank 1. So dyadic cubes of rank 1, they're cubes of edge length 2, and each one of them contains 4 basic cubes. Or in other words, 4 dyadic cubes of rank 0. I take the center of each of them, these x's, and I connect it to the center, like so, with tubes of, say, with epsilon 1. And then in the next step, I have 4 dyadic cubes of rank 2. Each one of them contains 4 dyadic cubes of rank 1. In one of them, we have a pre-existing structure here. In the other 3, I'm going to put a similar structure, but not exactly the same, because if it's exactly the same, I have the self-similarity issue. So it's going to be a little bit different. I'm going to use a thinner epsilon, say epsilon 2. And then I'll connect the center of each of these components with the center of the cube, like so, with tubes of width, say, 2 epsilon 2. And then on step K, I have dyadic cube of rank K. It contains 4 dyadic cubes of rank K-1. In one of them, we have a pre-existing structure. In the other 3, we're going to create something similar, but with thinner tubes. And then we'll connect the center of each one of them to the center of the dyadic cube by tubes of width 2 to the K times epsilon K. And in higher dimensions, it's going to look like this. So we start with a basic cube of, dyadic cube of rank 1. It has 8 basic cubes in it. I connect the center of each of them to the center of the dyadic cube. And then the next step, I'm going to take a bigger dyadic cube, so a dyadic cube of rank 2. And then this time it has 8 dyadic cubes of rank 1. In one, we have a pre-existing structure, the yellow one. In the other ones, I'm going to create a different structure. It's going to be similar, but the tubes, the green tubes, are much narrower. And I'm going to connect the center of each of these structures to the center. Now, notice that these yellow and green things, I'm going to call them leaves. They're very narrow. So basic cubes that interact only these leaves, they are good basic cubes. The rogue basic cubes, the bad ones, are the ones that interact, that intersect the branches. The branches are these brown areas that are wide, and I don't have zeros in them at all. So I can control the number of rogue basic cubes up to a constant by the measure of these branches, so the total measure of all the branches, basically. You may ask yourself, well, you are using narrower tubes later on. Why don't you just use narrower tubes from the beginning? And the reason is the narrower the tube is, the more you pay in growth. So we start with tubes that are not very narrow, just to not mess up with the growth. And the farther away I am from the origin, I can allow myself to pay more in growth because I'm farther away from the origin. So because we're looking at the asymptotic relative to R, it doesn't matter. And I think this is basically everything I wanted to say today. So thank you.
Okay, thanks very much. Are there any questions, comments? So maybe just a very simple-minded question. So if you could go back, so why do you call them frequently oscillating functions? Maybe I missed the definition.
Well, so in every basic cube which is not rogue, the function oscillates a lot. So if we go back to the definitions, here, see, I have these two properties. And if the function is bigger than 1 at some point, but it's also a lot of zeros, then it has to oscillate a lot between the two. Sure. And it's this oscillation that pays in growth.
Okay. Okay, thanks. Any other questions?